Awesome. Great. Genetic algorithm, because we totally haven't already started talking about this yet. So, Logan wrote, this is going to suck, and then I said, it's already spooky enough. We totally haven't been this before. Yeah? Great. Okay. So, this is the Wikipedia definition. It's confusing. Genetic algorithm last semester, Jesse gave us 2 reading materials. The link to the Wikipedia page and the link to tutorials point both had equally confusing definitions that don't make a lot of sense. So I can read this for you and it's going to sound awful. A genetic algorithm is a meta-heuristic inspired by the process of natural selection that belongs to a larger class of evolutionary algorithms. Genetic algorithms is commonly used to generate high-quality solutions to optimization and search problems by relying on bio-inspired operators such as mutation, crossover, and selection. John Holland introduced the genetic algorithm in the 1960s based on the concept of Darwin's theory of evolution. Afterwards, his student of David E. Goldberg extended genetic algorithm in 1989.
Did anyone understand any of that?
No.
Good.
Okay, so we got maybe 2 people that are like, I kind of think I get what it's trying to say, but everyone else is like, what the fuck is this?
And you don't get what you think it is.
Oh, EA, great. Okay, not EA Sports. Okay, so basically, this is awful, but I'm going to talk about it in the best way that I know how to explain it. To put this in short, the computer does a guess and check to find the solution. But what it does is it adjusts its guesses between generations, and I'll explain that a little bit later, by adjusting its guesses in a style similar to how evolution works. So also, all of these slides will be posted afterwards, so you don't need to worry about taking crappy photos from your phone while sitting at the lecture hall. You can just take screenshots once we upload it to the drive right after this. Awesome? Great. So basically, to continue on this, how does it work mathematically? Like, how does it just guess and check a solution? How does it figure this out? Well, you need a few different things. You need a data set that is the data that you want to actually, like, do something with and figure out, like, an optimization from it. You need a target type and a function to convert that data to that type. A target type, so target is a word that is used in the machine learning and deep learning community where you have data, which is your input, and target is what you want your output to be. Now that switches around on what data is where and that type of thing, but for genetic algorithms, a target type would be like if you had a bunch of points on a graph, your target, maybe you want to do a linear regression, so your target type would be a line, that type of deal. And then you have a loss function. So I'll kind of explain these things now a little bit more in depth. So a data set, this is the data. That's, if you were using genetic algorithm to calculate a polynomial fit, this would be a set of coordinates. This is, you have a bunch of x and y coordinates, and you want to go, well, you want genetic algorithm to figure out, like, what the polynomial fit is. So if you want a cubic function, you say, hey, here are my points. Your target type is a cubic function, and go figure it out and find out what that cubic function is. And essentially, that's what it's going to take, is it's going to take those x and y coordinates and try to figure that out. The target step and the typecasting. So this has a little bit more. This will be the data that is going into the actual fit itself. If you were using genetic algorithm in that example, it would be, you'd have a quadratic function. Let's say a quadratic function is your target. Your target may actually be that the right answer you want genetic algorithm to spit out is an array that's 4, 2, and 0, or let's say 0, 2, 4 in an opposite order. Depends on how you want to format it. You would be deciding that when you write it. And essentially, what that would represent is, that would be saying 4x squared plus 2x plus 0. And so essentially, like, you would have the form that you would know, okay, this is the target data that I'm trying to get to. Eventually, genetic algorithm should be able to get to this point where it knows that the best fit for this line is a line that has the equation y equals 4x squared plus 2x plus 0. Everyone kind of understanding that at the moment? Kind of, yeah, question? Yeah. So the target type in this case is if we had a bunch of points, let's say those points all fell on the line 4x squared plus 2x plus 0. So the target itself would actually be the data we needed there. The target would be an array of 4, comma 2, comma 0. Now you know that array is 3 long, so you know that if you were dealing with a polynomial, that you would have 3 different coefficients. Because if you remember in a polynomial, if you have like plus 0, that's actually plus 0 times x to the 0, which is 1. And so essentially what you would know is that, like, okay, if you had this in like the reverse, like maybe it would be better if I had formatted in the reverse so that 0 was at the 0th index, you would know it would be 0 times x to the index that 0 is at. Then you would know that like the 2 would be at the second index, or the first index, so you would know it would be 2 times x to the 1, because it's at the first index. You would know that 4 is at the second index, and you would say, okay, 4 times x to the 2, so it's 4x squared. Essentially, how you have to deal with this to figure out this math and do it is you need to hold this all in kind of arrays, or you need to keep it in a specific way that you can track loss. So to track loss, because that 420 is not going to start out that way, and the algorithm isn't going to know it. It just knows, well, here's some data, and I need to figure out what line fits it best. So it's going to have to randomly figure that out. Well, how does it know how far the random one it has is off from what the actual should be? Well, if you have a bunch of points, what is a way that, like, in your calculators, on like the TI-84 or any of the like Texas Instruments or a bunch of other calculators, if you do a quadratic regression, what's a value in your calculator that it tells you how good that fit is? Anyone know? Yeah. What's the letter for it? No. It's R. R and R squared. R squared is specifically a number from between 0 and 1, and that represents how good the fit is. 1 is perfect, and 0 is what is this line? And so, like, in that example, the loss is what R squared is. It's essentially figuring out, you'd have a function that would, in this case for a polynomial function, the loss function would be calculating the R squared of the line you currently have with all the points. Does anyone remember how to calculate R squared? Yeah.
It's the sum of the distance between the points squared.
Yeah, so I won't go too much into it, but it's basically that. It's what it is you're just looking at the distance from the points that you have to the line that you have and figuring out how good of a fit it is and the net distance from that line. And so you would look at it in an absolute aspect. That math you will need to probably look up for genetic algorithm if he has it structured in roughly the same way he had it structured last semester. But essentially, when you write a loss function, that loss function needs to handle, in this case, it needs to already have all of the points inside of it, and then it needs to be able to be fed a target type, so it needs to be able to be fed a line. So if we were dealing with a polynomial line, you would need, that loss function would have to take in a polynomial line and then figure out, okay, with this line, I already know that my data is all these points. Those points aren't changing, so that's already built into the function. And what would happen is you would just say, okay, for this line, the loss for this line with these points is 0.5. And the loss for this other line with these points is 0.6. Well, if one is really good, which is the better line? The second one, the one with 0.6. Yeah.
Will these formulas be provided, like
Most likely not.
Oh, jeez.
Most of these formulas are standard math formulas that you can look up.
Okay. Would you mind providing links to them on the slides?
You can't Google how to calculate R squared.
Well, I mean, like, I don't know, but like, because I mean, I'm not very good with stats, so.
So this isn't just a stats topic. This is a math topic that covers from a lot of things, and the fact being is r squared is a math topic that has been talked about in algebra and calculus classes, even if it hasn't been explicitly covered. It's not a particularly difficult equation. It's just dealing with the summation type thing. It's not a specific equation that you can just go, oh, this is the equation that I plug in. It's a concept of understanding you need to go through all of the points and then figure out the net distance from that line. And so it's looking it up and seeing how r squared is calculated. There's no definitive equation. What I just gave as the explanation is the best way of an equation. It's not like us saying, oh, you need to find the sum of natural numbers, and like it's me saying, no, I don't want to provide you with sum of I from I equals 1 to n is n times n plus 1 over 2. It's not me saying that. It's me saying like, well, it doesn't have a definitive equation like that, and so it's just Google and look up how to do r squared, because like that loss function as an example is not going to necessarily be this genetic algorithm. Jesse hasn't finished the document yet, and it's going to be up on Thursday, but like your genetic algorithm shouldn't be tied to a specific loss function. So essentially, the loss function is one you write for a specific data set. So this genetic algorithm, you will most likely, if it's like last semester, you will need to write a loss function that handles like 4 points. But in theory, you could feed it a loss function and a data and a target type of literally anything, and based on that loss function, the genetic algorithm will return what you want it to. And so that's where I'm going to talk a little bit more. Yeah.
So in addition, your question of can you put that on the slides and stuff, these are recorded. We are recording this week. So if you need to like hear about r squared again,
yeah,
just go back and
you can go back and watch back through again, and like YouTube's gonna have a million videos on how to calculate r squared. Like there's gonna be way better people at being able to explain how to calculate r squared than my like half-assed synopsis. Like the fact being, it's a mathematical concept that is not one that is super high up, and so if it hasn't been covered in your class, don't worry. It's not something that's like conceptually murderous to get your head around.
And on that, all the TAs know what r squared is. If you walk in and ask what's r squared, either we know what it is, or you can ask and we'll figure it out in 5 minutes and you'll know.
Yeah. Awesome. So, do people kind of get what loss functions are? You're nodding your head, and I know that like some of you are nodding your head just because, yeah, okay. So basically, like to continue one little bit more thing is loss functions tell you, you say, okay, I have this data that's changing, and the loss function takes it as a parameter. The loss function already has built into it the data that is not changing. So in the case of a polynomial function, we know our coordinates aren't changing. We're always trying to fit to those coordinates, so that's built into the loss function. Now, for the parameter for the loss function, what's the thing that's changing that we're like continually trying and randomizing? The line. And so the line is the parameter, and essentially what it just says is it takes that line in, and then it already has its data points built in, and it just goes, well, if I already have these data points built in, and I'm given this line fits it meh, or this line fits it with 0.6, it fits it with 0.7, and eventually what your goal is to get it to a loss function where, depending on how you set up your loss function, if 0 is the best fit, then you're trying to get your loss to 0, or you're trying to get your loss to 1 if 1 is the best fit. Yeah. R squared is an equivalence of a loss function for a polynomial.
But there's also linear functions as well. Hold.
Yeah.
All right. So, Jacob's really smart. I'm really stupid. So it took me a while to figure out what a loss function is, okay? Let me try and explain it in non-Jacob terms, because I see a lot of you glossing your eyes over and figuring it out. So over here I have a lovely graph. All right? So, genetic algorithm, we have these points. I don't know if you guys can see them. I hope you can. If you can't, make them darker. All right, can you guys all see the points or have a relative understanding of what points on a graph looks like? Cool. Okay. Yeah. Oh, actually, this works better. Okay, so I knew I put the slide.
So people on the stream can also see it.
Yeah.
Yeah.
Yeah. All right. Can I have my laser pointer?
Yes, you can have the laser pointer.
All right. So we've got this. So this is a line of best fit, right? So our function, our loss function, is going to be how off this line is from being correct. Okay. So if I took a line, what is the best way to do this? If I took a line like this, that's not going to work. That's not the best way to do it. Okay. If I took a line here, right, and put it here, this would have a bigger loss function than this would. Okay? Actually, paint's not a bad idea. Going back to our old trusty friend MS Paint. Okay, so I've got this red line here, and I've also got this black line here. Okay? So obviously from looking at this graph, we can see that the red line's a better line of fit, right? We all get line of fit to that degree, right? And black line is worse, because it doesn't come near like half the points, right? So what we want to see, what the loss function is it's a function that tells us how off that black line is. So basically, how close are we? So this will have, theoretically, don't quote me on numbers here, please. This will theoretically have a loss function of like 3, right? This being 0, okay? Okay, so this will have a loss function of 1, right? So this is like as bad as it could be. It's anywhere close, right? But if I draw another one here, which is better, it's not great, but it's better, right? So in orange, right? This will have a loss of like 0.3. So you know you're getting closer. You're aiming for 0 here, right? And then if I draw another one here, right? So real close, right? This one's in a light blue. That's going to be an even smaller loss function of 0.1. So your goal is to get as close to 0 as you humanly can. Yeah.
So basically we're doing a linear regression, but we're given the line of best fit and we're just trying to like find.
No, you're not.
No, you're not given
the
line.
best fit.
Your goal is to find the line of best fit. But a lot of finding.
The line of best fit.
Correct.
Yeah.
Given how close it is. That's what I'm
So
Well,
a lot of programming the line of best fit is guess and check to see if this is the line of best fit. So what your code has to do is it has to return how off is this from the line of best fit. Like how well does this fit? That's what we're going for. So imagine the red line didn't exist, right? So these were our tries. Our try was black. Okay, that's really off. Let's try like way in the other direction. So then we tried orange, right? And that was better, but it's still not great. So let's keep trying another number.
So then
Keep checking to go to blue, and then we see, oh, that's close, but that's not exactly it. And then we go down to green, red. Stop changing color to me, man. We go down to red, and then we go, oh, this is right. So that's the point of genetic algorithm as a whole, right? So the loss function is specifically what is telling you how off are you.
Yeah, so like after it hits the blue, it may be really close to red, but it may randomize it in a way that suddenly it's now like that.
Yes.
And it just might be like, okay, well that, and it looks at the blue and the green, because the green is now the one that it randomized a little bit, and it goes, well, the green is not really better, so then it then tries in the other direction, which then has it go back, and it goes, oh, okay, so I think I still need to keep it this way, and then now what it gets is it gets like that. And then it goes, well, I think green is a little bit better because it's now kind of going through it, and it keeps just changing this line around in minute ways when it finds something that works better, and it just keeps moving it around until eventually it gets exactly to the point of boom, it goes, I found the one, and then it keeps trying a few more, and it goes, I can't find anything with a better fit than this that are slight variations around it.
Okay. So does everyone understand that? Okay. There is another part to this. Okay. No. Nah. I assume you're going to go over this other part, but I'm going to go over it now. So the other part is these are all straight lines. There's a lot of time that you're not going to have a straight line, right? So if you've got a chart here, right, and you got like point here, and then like a point here, and then like a point over here, and then a point up here, right? Your line of best fit could be a polynomial, okay? So your line of best fit could be this, which is a really awfully drawn polynomial. But it could be a polynomial. So that in that case, your loss function is going to have a couple more things. So your linear function is going to be in y equals mx plus b, right? You're going to be changing your m value, you're going to be changing your b value. If it's a polynomial, you're going to have to change more values. So you're going to have to change that the x squared value, the x value, and then your addition number value, right? And this can go up to, was there ever a cap on how many powers it could go to?
With the amount of strength that your computer has and the amount of time it takes to do a polynomial, because of the restrictions on AutoGrader, I think the max size he ever had it run was a cubic function.
So 3, right? So you can have a 4-variable function.
You have 4 different variables because you also have the coefficient.
Yeah. So you can have a total of 4 different variables within your functions, right? So it's not just going to be linear. We did a linear example because that's easy and easy to show. But just know that your loss function is going to be a number between 0 and 1, but it's going to depend on what kind of line it is. So it could be a cubic function, it could be a polynomial function, it could be a line, etc.
So like, also to lead off, which is why when like I was hesitant to say yes when asked, so we're coding a linear regression, because if you scale a linear and then you say, oh well, we're coding our polynomial regression, no, because genetic algorithm itself is not a polynomial regression. It's not a linear regression.
Yeah. So speaking on that really quickly, let me add. You won't be told if you're looking for a polynomial or a linear or a cubic or just a number, right? You won't be told what you're looking for. That's what we're talking about with iterating. So here, when Jacob made each of these lines, right? So go through all the linear and goes, none of these are really great. Let's try polynomial, right? So you'll create a polynomial starting at one point, and then you go, is this better? Well, let's run through all of these. And so you'll run through everything because this set of points works really well with a linear function, right? But there's other sets of points that work better with qubits or with polynomials or just
Last semester
numbers.
he did tell us how many orders that it was going.
Okay, never mind. He will tell you how many orders.
That one, yeah. Well, no, that was built into your loss function. The genetic
yeah,
algorithm
yeah.
itself was never. So essentially, like genetic algorithm, what I'm talking about, where it's like you're calculating loss. That loss could be literally anything. In this case, for a linear function or a polynomial function, that loss is your r squared. But your loss is literally any number that is telling you how close you are to the actual fit. Because the computer doesn't know that it's computing a linear. It doesn't know if it's computing a polynomial. It doesn't know if it's computing what animal would be the best fit in a ecosystem. Like, if you took let's say a kangaroo and you threw it in Antarctica, what would be the loss function on that? Would it have a good loss? Like, would it be a good fit in Antarctica, or would a kangaroo in Antarctica be a bad fit? A terrible fit. And that's what the loss function would say. Now, your computer wouldn't know if it's looking at a kangaroo or if it's looking at a penguin, but it would know that if it passed through the genes for a penguin and it passed it into the loss function, would the loss function be closer to 0 for a penguin, or would the loss function be closer to like a worse fit than the kangaroo? The better fit would be the penguin, because if you don't, because it would just say, oh, well, the penguin's a better fit for this, and then the code would adjust and say, well, this where I created a gene that represented a penguin, well, actually, I think the penguin's a better fit, and that type of deal, where that's where you have a bunch of numbers involved, and it's constantly just guess and checking, and so that's where it's just creating a bunch of different things that may have something very similar, and so kind of how this is shown is in a flow sheet. And so, yeah, I kept it. I kept the stuff you added into my slides. Essentially, what we're talking about is the initialized population. That's like if we're saying, oh, well, we have, in the case of what I was just talking about, that's like saying, well, our population is Antarctica. That's the ecosystem. Or the population is all of the data points that make up the thing that we want to do a linear fit for. The population is the points that we want to do a cubic function fit on. And essentially what it then does is it goes, well, the fitness calculation. So you have your loss function, and you say, well, based on these random things I just generated, so let's say we randomly generated a kangaroo, it puts the kangaroo into the loss function, which is already set up for Antarctica, and the loss function goes, why are you putting a kangaroo here? And then what it does is it goes, well, we're not terminating because that's not a good fit at all. The loss is like, let's say 0 is best fit, 1 is worst fit. So let's say a kangaroo is 0.85. Well, that's, if we're trying to say let's get within a fit of 0.01, is 0.85 less than 0.01? No. So then it's going to continue on, and it's going to take, okay, this kangaroo, it's going to mutate, and it's going to keep changing it and go, okay, we're going to change the kangaroo a bit. We're going to like do some weird stuff to it so that we create like 10 copies of the kangaroo, all with slight variations. And then it's also going to throw in like a few other random animals. So let's say it throws in a bird, a sea turtle, and an antelope on top of these variations of the kangaroo, and it goes back through and it goes, well, let's compute the fit for all of those. Well, out of all of those animals we just list, what's going to be the best fit for Antarctica? A bunch of random kangaroos, a sea turtle, or a bird? A bird. Because do sea turtles live in Antarctica?
Regardless,
No.
not a kangaroo. is the correct
Not a
answer.
kangaroo. But it just randomly was like, oh, well, I'll choose this random animal, which is going to be represented in numbers. And it goes, well, this is a better fit. And so now it takes the bird and goes, well, it's still not within the result range that we want. So then it goes back through and it mutates the bird. So now we have an ostrich. We have some weird other like chickadees and stuff. And we have a penguin. Well, now it goes back through after doing that, and now it has a bunch of random animals. So it has some variations on bird, and then it also has like another weird, like it has a deer, a horse, and a dog. And it goes back through and does the fitness, and then it goes, wait, a penguin's a really good fit. And then it pulls a penguin, and then it keeps doing that until it gets the best penguin that's a fit for that ecosystem. And when it hits that point, it goes, yes, let's terminate because we're within 0.01 loss. And it goes, here's your emperor penguin, rather than a puffin, because a puffin's not going to fit Antarctica very well, but an emperor penguin would. Yeah.
So, like, for, like, the kangaroo and, like,
Yeah.
generating these animals, like, is this pool of, like, let's say animals that
Yeah.
we're pulling from, is this something we're going to be given, or is this something that we would need to, like...
To test, you are going to need some of your own tests. When I say animals, all of these animals and all of these things are represented in numbers. They will never actually be represented as saying an animal, because the computer doesn't know what to do with an animal.
Well, yeah, but I mean,
And-
like, a
yeah.
pool of numbers,
Yeah.
for example, but that set of data
Yeah.
that we're pulling from,
You will create it, so if you're trying to test it against a polynomial function, you'll choose your own coordinate points that you know if you do a regression on as a quadratic regression, it returns as x squared. And so you would like come up with your own points for testing and that type of deal. You may be required to actually write the functions for polynomial and linear regressions and not just the genetic algorithm itself, so that you are forced to do some testing with that. But most likely for the primary objective, Jesse will only run your genetic algorithm. Yeah, question.
Yeah.
Yeah, and so that's
So
the randomization.
Yeah, so specifically this had to do with Darwin, right? So this whole thing came up about Darwin's theory of evolution, right? So only the strong survive, right? So if you think about it like that, it's you put two against each other, well, okay, this one survives, so it's a better fit.
Yeah, and so that's kind of where it's like, where we say you're going to mutate the kangaroo a bunch of times, and then you're going to throw some random other animals in the mix just in case the first random guess that it did was nowhere near what it should be. You throw a few more random guesses in there so that you have a chance of hitting something else sooner, rather than having to mutate your way from a kangaroo to a penguin, which genetically speaking, they're connected, but are they connected very closely? No. And so you'd have to go the long way, but if you throw in some randoms, you're more likely to randomly generate something that is much closer to what your actual fit is. Sam, you had a question? So that's where you start dealing with functions that are like random functions that will like, because they will all be represented as numbers between 0 and 1, I believe is how Jesse had it set up last semester. That essentially you treat numbers between 0 and 1 as actually a range of negative infinity to infinity. And so because all of these are numbers and they're a bunch of set of numbers, you just know that you can do a random number generator, but you can also say, well, if I have 3 and I want to mutate it slightly, if we wanted to give it like a little bit of a range, we say, well, we're going to multiply it by a difference between negative 5% and 5%. So you take 3 and you multiply it between a random number that is between negative 5% and 5%, so you know that there's the max change that you could have is plus or minus 5%.
So there's a random number generating method.
Yes.
That would
Specifically in Scala, the random method is you import random and you assign random as a class. And so once you have that, it is specifically when you call random.randint, you can give it parameters between what integers you want it to do, or you can call a different function and have it immediately just give you a random like double between 0 and 1. So there are functions to do that. You will not have to code the random. You will not have to code the specific function that randomly generates a number between 0 and 1. You will have to use that function to like selection, crossover, and mutation.
Okay. I'm going to stop Jacob from his tirade for a second. Okay? When you guys are finishing the rest of this lecture, review session, whatever this is, right? I need you guys, so this is a specifically conceptual review session, right? So don't worry about how you're going to do it in Scala. Don't worry about exactly the syntax, how you're going to make each function. Worry about understanding the concept of genetic algorithm, because once you understand the concept, the code will come a lot easier.
Yeah.
Okay?
Like the document is going to have a lot of the implementation laid out, and so if you understand what a genetic algorithm does, not in the aspect of code, but what it says, here's a kangaroo, and it mutates a kangaroo and breeds a kangaroo, and then also throws some random animals in, and then it chooses from those animals which has the best fit. That's the understanding. We'll talk more about implementation stuff probably next week.
Next week, once the document has been released, and once you guys have a little bit of a generic idea.
Yeah.
Ha, generic. Before we get to the next slides, because the next slides are a little different.
Yes.
So the next slides are a little different. Before we get to that, just a couple tips for generic algorithm, and then genetic algorithm, not generic. I'll answer questions after, okay? Just a couple tips. When the document comes out on Thursday, take a time between then and the review session, right? If you guys are planning on coming next week, we're going to talk about genetic algorithm again. Basically, next week's review session. This is what happens when you give Jacob a laser pointer. Basically, next week's review session is going to be exactly the same. Only we're going to go over the level 3 quiz instead of the clicker quiz. And then we're going to do more genetic algorithms. This is a big topic, and this is going to span a lot of the time. So come in with it read. Basically, read the whole documentation, go through, highlight it.
Put questions in the margin
Yeah,
so you
please.
can ask us questions about what you want clarification on.
Please do, because we're here to help you guys. We both, at least at some level, kind of know what we're doing. At Jacob's level, actually know what he's doing. So like, please come with questions and stuff, and like knowing what you're doing. Don't just expect us to teach you genetic algorithm, right? There is some amount of self-learning on this. Jesse's gonna put a couple links with it. Make sure to read the links. Make sure to, you don't have to like take notes on the links, but like make sure you read the links. Make sure you know what it's talking about, and pull the repo, right? If there is, which I believe there is.
Pull the repo immediately.
Pull the repo before you do anything else, and make sure you understand what the code is there and what the code that he gives you is trying to do, right? You don't want to create 7 different kinds of duplicate code. We've been preaching this stuff for the whole semester, but it didn't really matter up until now. Like clickers wasn't super difficult. The extension wasn't super difficult. Calculator wasn't super difficult. This is where it starts getting to the big time. This is where everything becomes really difficult for a short amount of time, and you guys just gotta focus and buckle down. Right?
116 is a gradient between 115, which is hold your hand in Python, and
220.
goes into 220 and 250, which is
rough.
code in a very low framework language with large tasks, and it's very conceptual, and you also have to understand the supporter code that you do even before you walk in. You have to know exactly what you need to code before you start coding it. It is much less you can just put your hands on the keyboard and code it without like actually fully understanding and then just tweaking it to work. That doesn't fly in some of the later classes, and 116 is part of this gradient into that so that we don't shock you too much. Yes, there is some shock. Yes, this isn't like, there are some leaps and bounds we're doing here. It just needs to happen, but that's also why we're trying to make sure that these review sessions are talking a lot about genetic algorithm, because we want to give you guys the support we didn't have last semester.
Yeah. What Jacob said. Right? Okay, so, like, make sure next week when you come here, if you come here, which I would, again, highly suggest, make sure you come with the documentation read, make sure you pulled the repo, make sure, like, we've gone over what a genetic algorithm is. I don't expect any of you to understand this, right? You just got a really obscure topic thrown at you, okay? Read the documents, go through it. Even if you don't understand that, try and make sense of, like, at least a little part, right? Take it chunks at a time. We're going to go over again next week what a genetic algorithm is for anyone that, like, wasn't here, right? So we're going to go through it again. So make sure that you have maybe a small understanding, so that way when you're here, you can get a better understanding of the rest of it. Okay, questions, we're going to go there and then there.
Actually, like, there's one other thing I want to add, that there's a video on YouTube about genetic algorithm in Scala. Like a whole 15-20 minute video.
Cool.
on it.
We're going to have to find
And
that
it's
video.
also
We're gonna find that, because if there's any code in there, we need to
Yeah.
double check
Yeah,
it. Because
so-
if you use any code from
There.
something that is a online resource that is not Scala documentation and
Yeah.
not provided by Jesse, that gets into very much academic integrity territory. And
be-
so,
I would stick to not Scala specific stuff. I'd stick to just generic genetic algorithm. Like,
any resources we give you at the review session, any resources Jesse
Jesse gives-
gives you, and any resources that are on the Scala documentation website
Or-
are the only resources you are allowed to use for this.
anything we post on Piazza as well.
Yeah,
If we put a
any-
link on Piazza or something, that's
That's
fair game. Right? Okay. Yeah.
So for like, seems like it's gonna be a grueling test programming.
It's gonna be rough, man.
So like, is there any recommendations on the programming aspect, like ways to
Start
get
That'll
early.
be talked, like, start early.
So there's a couple things we can say before the document comes out, but then there's stuff that we'll say next week.
Yeah.
So start early. A lot of people didn't do Clicker until like the last minute, right? I think you made like a very
We loved your post.
he made a
Very,
very
very
upset
upset,
post, right?
Jacob was very sad.
Jacob was
office hours.
okay. Jacob was very upset, but we were all kind of a little upset that you guys started Clicker really late. Start this one super early. Like however hard you thought Physics Engine was, which I think was the hardest one that you guys have had so far this semester,
Yeah.
right?
I agree.
However hard you thought that was, this is harder. This is rougher. This is worse. This is gonna make you want to quit CS. It's just this is how it is. It sucks.
And then we're going to talk about the Wave genetic algorithm right after this. It's great. I love it.
Okay? But it's also really cool, and it does a really
Yeah.
cool thing, and once you understand it, you go, oh my god, this is awesome. Right? Stick with it. Right? But start early, because if you don't start early, you're not going to get it. And you, most of you here, I recognize you from at least coming to my office hours, and Jacob probably recognizes the other half from coming to his office hours, so I don't really need to tell you guys this, but make use of the TAs. A large chunk of us know what genetic algorithm is and how to do it, and if not, we're having a TA review session to make sure
Is Jacob running it?
Jacob and I are gonna run it. Yeah, we're
We're doing what now?
I'll tell you about it later.
Okay.
We're having a TA review session so that way the TAs know what they're talking about, right? So everyone will know what they're talking about. Don't be afraid to go and ask them, because we get paid to be here to help you guys to do this. Abuse us, please. Just not after the hours.
Actually abuse me.
Yeah,
I'm
that's
fragile. I hurt myself a lot. Like, you guys remember when I was in a sling?
yeah. I'm like a 40-year-old, remember? All right, that's my tirade.
Yeah. So like I have a bunch of office hours, guys. Like I have the hour right after this. I had 1 to 3 today. I have 1 to 3, 5 to 7 on Thursday. Like I have 6 to 8 tomorrow night. Like or 6 to 7:50 because I have a lab at 8 that I run. But like I have so many office hours, and a bunch of them are evenings. So like with genetic algorithm, like I'll be there, and like odds are if the document gets released Thursday morning, there probably isn't going to be a whole lot of you here Thursday night, but there should be, because that's like, you just got the document, and if you just started, like if you just finished classes and you're like, well, I haven't even read it yet, well then, that's okay. Come to the office hours and just start reading it at office hours with me, because if you don't understand it while you're reading it, I'm immediately there and I can immediately answer it. And if it's Thursday, like, there probably isn't a lecture question due. It's just at the beginning of a homework assignment, and that means there will probably be almost no one there, and so we can just talk about the document and explain where you might be confused somewhere, and I can just walk you through it. And like, that would be a great time. Yeah.
Also, when is demo 3, like the specifications?
So, can we say anything?
I thought it got announced in lecture.
Okay, so let's announce it again here. So, there was... Yeah, so there was originally plans to be 4 different demos. There's now only 3 different demos. Demo 3 will be later down the line. It's not at the original due date of Demo 3, whatever
I think
that
it's at the
was.
demo.
It's at the Demo 4 due date.
Right. Oh, when are the specifications for that?
Not yet.
I didn't, okay.
Not yet. I believe that's like in like 4 or 5 weeks.
Jesse is staying
Jesse-
up late at nights trying to get all of, like, get genetic
Yeah.
algorithms, new document finished, and get all of that. He's trying to, like, get the demo 3. He is working so unbelievably hard. I get that some things are coming out a little bit late. I get, like, a lot of things are, but Jesse is working so unbelievably hard. All of the auto graders, when he writes a new homework assignment that is different
writes a
from
new
last,
auto grader.
he has to write an entirely new auto grader. So essentially, for every new homework assignment,
He
because
does the homework and then does the inverse of the homework.
Yeah, and he has to write incorrect solutions so that you can run your tests against incorrect submissions. He has to write the autograder itself. He has to write the correct code. He has to write, like, every test case under the sun that he can think of so he doesn't accidentally give you points when you don't have working code. Like, he has to come up with all of these submissions and all of this stuff, and also the demo 3, and he's working so unbelievably hard.
Okay.
Yeah.
Chill with the Jesse fan club, okay? I love Jesse. Jesse's great. Okay. Okay. But I believe it's also he doesn't want to overwork you guys, so he doesn't want to throw genetic algorithm and the demo at the same time because that's a huge amount of work. For right now, focus only on generic algorithm. I'm more than happy to look up the specific date for demo 3, but it's gonna be in a while. Don't super worry
just
about
like,
it.
am I gonna have to worry about this?
End of the semester.
For right now, don't worry about it. Even if it comes out while genetic is coming out, focus on genetic and then do the demo after. You guys got plenty of time.
It should be end of the semester, roughly, is when it's due, and
Yeah.
so, like, you have
Correct.
5 weeks
Also-
at this point, and once it releases.
Also, before we get into Jacob's thing, lab this week, if you haven't been already, lab this week is kind of chill because we've thrown a lot at you guys really quickly, and it's like mental health. Cool. So come in. If you haven't read the lab already, read it. Basically, I'm going to give you TLDR. We want you guys to come in and just ask us a question. So
Like a thoughtful,
actual question, not just like how your days go, how is your day going, but like if you have a topic question. So like if you didn't understand like WebSockets, ask us about it. That's what we're here for, right? So I think it's either or is it and? So you need to come in with a question, right? And a personal project idea. So if you wanted to do something during UB hacking, just tell us what it is. If you had an idea for, I don't know, a robotic butler that does something, tell us it. Just tell us an idea. If you're already working on a personal project, great. Tell us the personal project. We want to
hear this stuff that you're doing cool shit outside of the class. Like, also employers like to hear that, and we like to hear it.
Right. So this week is a chill lab. There's no coding involved. Show up, talk with us. You're more than happy to show us your personal project. Just only show to Joe. But joking. Regardless, this is a chill week for lab. You guys have the quiz tomorrow. Study for the quiz, but don't worry about lab this week. You guys will be done way under the 2-hour mark. In my labs, if you want to come with gaming equipment, I'm just going to be there for 2 hours playing games. If you want to join, go for it. Go for it. But most labs are going to be 20 minutes and then you're done, and then the TAs will be around for 2 hours. So if you just want to chill with them, go for it. If you want to ask questions, you want to bounce ideas off of them, go for it. We're there for 2 hours regardless.
If you show up with actual questions and you show up with a project idea that you kind of thought up, like, the fact being is you're going to get full points. It's going to be a great time. The point is, like, we recognize, and we saw from the lecture question last week where you guys gave feedback, like, a lot of shit is going on, and we get that a lot of stuff is going on, and it's a lot being thrown at you, and college is a lot, and like we feel that too. Like we
Yeah.
have
Also,
a bunch
we're
of
we're dying as well. This is not just a you guys thing. Rough.
rough.
Like we had 2 midterms really recently that were rough. So we understand that you guys are dying because we're also dying. So this is a break for everyone involved. Okay, take advantage of it. Actually, come to lab this week. This is a free 25 points. Like
Yeah.
there's not much more we can do.
You
to
show up
give
and
you points.
you
You show up and you talk with us for 5 minutes and you get 25 points. It's the easiest 25 points you get all semester. Okay.
awesome. So
Have fun.
yeah, I'm going to talk about why genetic algorithm is so cool. So like, I kind of touched on this at the beginning, which is I worked with like machine learning and neural networks and deep learning stuff, and what genetic algorithm is kind of similar to is a neural network. So what is a neural network? By the way, all of this stuff that I've written isn't off of Wikipedia, isn't off of this. This is from me doing copious amounts of research with this and kind of thinking up the best way to explain it to you guys. And so like it's an algorithm that you write, an algorithm being just a set of code that is loosely based off of the human neural system. So kind of how your brain interacts with different other parts of your brain is when you pass electricity through a specific neuron, it will then, based on the frequency that's put into the neuron will then send a different frequency out to other neurons based on that neuron's property itself. And so it just kind of releases electricity based on the electricity it got sent in at a specific number. Don't worry too much about it. Essentially, it's just doing some math. Your brain does math without you realizing that's just with electricity, versus the code will do its actual math. And what it does is it figures out calculations that it needs to do without actually being told the math that it needs to do. It just does that same thing that genetic algorithm does, where it kind of does guess and check, and it plays around with some different weights, which is how it changes the electrical signal when it goes through. Those are called weights. And it kind of plays around with these and plays around with all the neurons it has to figure out how to get the data from what you have and what you want to be, and figure out how to do that math. So you may not know how to do the math, but you can have the algorithm kind of just keep doing guess and check until it figures it out. And so with that polynomial function, where most polynomial functions are y equals and then whatever the actual equation is itself. And so in this case where we were talking about kind of like where the target was the line in genetic algorithm and the data was the x and y coordinates. In a neural network, what we'd actually have is the target would be the y values. So we know what our answer should be. We know that we should get to a y value when you pass it through this algorithm. And we know that what we feed it is the x values. So if we have, let's say, a linear equation that's just y equals 2x, then we have a point that's x is 2 and y is 4. So we know that if we feed the network 2, once it goes through all the network, once it goes through all the neural nodes and all of that stuff, what outputs is 4. And the code is essentially going to play around with its numbers until it can get as close to that as possible. And so if you have a bunch of points that are roughly around the y equals 2x line, it may not be able to get perfect for every single point, but it may be able to get pretty close. And so what happens is, it's the same idea of genetic algorithm. It has to first, when it first runs for the first time, it is literally going to randomly do something. It's like if you were trying to teach a robot to throw, and all you told it was, you need to get the tennis ball from in your hands to in that trash can over there. You told it nothing else. And all it's able to do is track where the tennis ball is, and it's able to move its arm around. And so in that case, the robot's first thing it may just do is it may just move its arm in the direction of the trash can and then release the ball. the ball's going to drop and it's going to go, well, ball's there. It's going to be a sad robot. And so what's going to happen is now it's going to try, well, what if I hold it over here and then move it like that? Well, it knows that the ball now went a little bit over there, but it didn't go much farther. And eventually, while it's trying these random things, it noticed that, well, if I move it while I release the ball moves. And so it might know, well, maybe if I start pointing in the direction that I release, well, now the ball went where Logan is. That's still not the trash can, but essentially, like, it's getting closer and closer, and eventually it'll get to the point where it goes, well, I need to do this thing, this thing, this thing with my arm, and if I do that, the tennis ball goes in the trash can and everyone goes, woo. Woo! Happy robot. And so it's kind of that guess and check on what a neural network does. It doesn't know exactly what it does, because, like, does a robot know that it has an arm? But it doesn't. It just knows, well, I have a servo here.
No, it doesn't even know here. It just knows I've
Yeah,
got
yeah.
3 servos
Yeah,
and they can move.
Yeah, it has like 3 servos or like 2 hydraulic things.
It just knows it can move these things.
Yeah,
That's
and
all
it
it
knows,
knows.
it knows that like hydraulic can be at 0 to 1. It can be between this thing, like 0 is collapsed fully, and it can be at 1. And it knows, well, and then this one can also be at 0 to 1. And it can move them between those 2 points. But it doesn't know, it just has to try things until it gets the right combination of moving all of those 3 hydraulics to actually get it to throw. And so that's where just it keeps guessing and checking, and watching, okay, well, the tennis ball made it there. The target, which is the Y value, is that trash can, and what the actual Y value is where the tennis ball landed. And so what's the loss function? It's the distance between where the tennis ball hit and the blue trash can. Yeah. Yeah, so part of coding a neural network is writing that loss function. You need to be able to give it data, and you need to be able to give it, okay, based on the data that's both the data and the target, based on, so if you know, okay, the tennis ball is here, and the tennis ball needs to be there. Based on those 2, you need to give it the function, well, how do you calculate the loss? Well, in this case, the function would be, well, okay, the loss is where the tennis ball ends up, and the distance from that to the trash can. That's the loss function there. The loss function would be a predetermined way of basically you can give it what the actual Y is, and you can give it what the predicted Y is for that, like, throw. And it would say, okay, well, the distance is that much. And it would know, okay, well, where it just let go and it was a sad robot, that ball over here, that was awful. But it knows that, well, if it kind of did this and where Logan was, it knows, well, that's a much better throw than the first one because the distance was shorter. And so that's where it kind of, well, then it tries to throw it this way. Yeah. Yeah. And so that's what loss is. It's the error margin. It's figuring out how much it's off by, figuring out how close it is to the real solution, because it has no idea where that blue trash can is. It doesn't have a camera that knows, like, oh, the trash can's over there, so I need to point in that direction. It just knows where those 3 servos in its arm is, and it just knows where that tennis ball ends up after it does something. Yeah. Yeah. Once its distance is exact, it would know exactly the hydraulic movements it would need to do to get that tennis ball into that trash can. And so what would happen is as soon as it hits that trash can, as soon as it minimizes that loss so that that error margin is 0, it can perfectly repeat that every single time, which is the awesome part about a neural network. So, yeah, that's the loss function. I was talking about that. Okay, that's all my slides on that. But yeah, once you minimize it, like once you find that perfect thing, you now have a robot that knows exactly what it needs to do to throw the ball into the trash can from this point. Now, did you teach the robot how to throw a ball? Did you tell it anything about physics? Nothing. That's the awesome part about neural networks.
They learn without you telling them any information.
Yeah. It does guess and check, and once it figures out, okay, well this does less error, this does less error, and it keeps trying to go to less error, and then it finds the perfect thing. You can look up on YouTube, there was a robot where they put rollerblades on the 4 bottoms of its feet, and it was a quadruped robot, and they put 4 rollerblades on the bottom of its feet, and I don't think they told it anything about it. They just said your goal is to stay upright and move forward. And essentially, it just kept doing trial and error until it taught itself how to rollerblade. So you know how essentially the first time you rollerblade, you just stumble all over the place and you smack your face on the ground a little bit, and your friends point and laugh at you,
This
or
is
like
just you, man.
yeah.
Like we're going back to some more childhood.
But like you hold onto the wall and you're trying to figure out how to figure out your balance. You're learning yourself. The robot does exactly that too. It just knows I need to keep myself upright and I need to go forward. And then it figures it out. And that is the awesome part of what makes genetic algorithm beautiful. You don't tell it, hey, find a polynomial regression. You don't tell it, hey, find a linear regression. You just say, minimize the error, and eventually it figures out exactly what it needs to do. Because like, you could calculate what a regression is using linear algebra, but do you know linear algebra? Okay, besides
Be
you.
quiet.
Does anyone else know linear algebra? Do you want to learn linear algebra for genetic algorithm?
The answer is no.
The answer is no.
The answer is definitely no.
HPCs are so fun.
But
This is why you don't want to learn linear algebra.
and so that's the point is rather than learning the math itself, you can have the computer code it. Well, imagine it this way. What if we didn't have linear algebra and we didn't know, let's talk in a higher concept. What if we were trying to solve a math problem that we know we want to get this value into this value, but we don't know how the math, like what math to do for it? You could give a neural network, hey, here's your data, and we want it to eventually be this, so that essentially figure out how to do that math. Now, it doesn't have any concept of like summations or Newton's laws or anything like that, but it will try to figure out to see if there's a way to do it using its neural network properties. So it may not output an equation, but it will have a model that you can feed it in the value you want, and you get out the value you want every single time. So if you haven't necessarily calculated everything, you now have a calculator for that. And that is an awesome thing. Essentially, imagine it in an idea of an image. If we have an image that's, let's say, a color image, and we convert it to black and white. Now, if we wanted to take that black and white image and convert it back into color, can you do that?
Yes.
Are you magically able to just convert a black and white image back into color?
No, but I know you can because I saw those documentaries where they're like, we recreated it.
Well, that's
And that's
They're
this
guessing
is
now.
this is neural networks. And so what it is it looks instead, because you can say, okay, I can take a color image and convert it into a black and white image, you have the pair. You can go from one direction to the other, but because of entropy, you can't go the opposite direction. Like you don't physically know the math you can do to get a black and white image to turn into a color image. You can do the math the opposite direction, but you can't do the math that way. But you can feed the neural network a black and white image and say, here's the color image of that, get it to that. And what the neural network does is it tries to figure out what math do I need to do to get that black and white image to become the color image as close as possible. You train it to know, oh, well, if I find this pairing of pixels, it's normally this color. If I find this pairing of pixels, that are on this grayscale, it's normally this color, and it figures it out. And that's so fucking cool. And like, there's so many different things that you can look at in all of these. Like, I urge you that if you have the time, look at different neural network models. Look at a specific thing that I'd recommend is called the Pix model. P-I-X 2, like the number 2, P-I-X. It is so freaking cool, and you can see so many cool things it can do and how you can train it, that essentially what they do is you give it something with less information, and you then say, get something with more information, and it figures out a way to fill in those blanks. And that is why all of this stuff is so cool, and why I couldn't wait to talk to you guys about all this stuff. That like, yeah, a lot of you are going to be doing genetic algorithm, and you're going to dread it. But once you finish it, once you see how it works, notice how beautiful it is, and it's great. And like, I guess like, yeah, I'm fangirling about this whole thing, but it's a great, awesome thing. And I think let's cut it so that y'all can ask me actual questions if you like want to ask questions.
All right, so we're gonna end a little early, right? So it's 6:30. I got like 2 things to say, and then if you have questions for UB hacking, come down here while I do that. While like I'm here. Hold on, don't pack up yet, okay? If you have questions for UB hacking, come down here while I'm packing up. If not, if you want officers, just walk with Jacob to Davis. Couple things about what's coming up in the future, right? Okay. So next week's review session, there's 4 review sessions left. I just want to go over what's going to be in each of them, so you guys have a general idea. Next week is going to be more genetic algorithm, quiz, and if we can go over, it's going to be a little bit of linked list. You'll know what that means next week. Week 12, so that's 2 weeks from now, right? So next week's week 11. Week 12 is going to be probably a little bit more genetic algorithm, but we're going to kind of keep that open for right now. I've got an idea for a review session I want to do, but we'll see if that happens. Week 13 will be on graphs and review for the level 4 quiz. Week 14 is Thanksgiving break, so go home, we're not having review. And week 15 is the review week. That might be the one that I want to do. If not, we'll just do kind of general review during that week, just so that way you guys know what's coming up. Okay? Cool? Get out of here.